Alrighty, we are back with the JVC W-VHS deck. Ow. Oh, that's a big cut. I'm okay. So we're back with the W-VHS deck, and in my last video about this heavy and dangerous bad boy, I was probing around inside, looking at it on my oscilloscope, and I made this comment that it would be fun to decode the video directly off the analog pathway. And I said, I didn't have time for that. But that comment went out to the internet, and very quickly, one of the maintainers of the VHS Decode project reached out to me and said, hey, would you mind opening that thing back up again and doing those captures and recording them and contributing to the project? And I thought, sure, why not? If you're not aware, the VHS Decode project is a collection of enthusiasts and archivists who are really dedicated to getting the highest quality copies of analog media like VHS, Betacam, Laserdiscs, other things in archives. And the way that they do that is by recording the RF signal directly off the tape head or laser head or whatever the case may be, and then using computer software to decode it and get the video files out, rather than relying on the old and sometimes not great analog circuitry inside tape decks. So I've made some destructive modifications to my hand and also to the back of this unit to now have these 4 taps coming out the back here. I don't have the back panel on, which is why I managed to cut my hand on this sheet metal. But we have 4 taps coming out here that I was able to hook up to my oscilloscope and take some recordings. So in this video, we're going to decode the video. We're going to show you how to do that. And I'm going to start off by answering a question that caused really a lot of debate in the comments and also over on Reddit, which is this thing even HD? So we're going to spend some time talking about what HD is, how W-VHS lives in the HD landscape. And in the second part of the video, we're going to talk about some RF theory, how the FM encoding works, the trade-offs that are made there, Carson's rule, beta, a whole bunch of things like that. But let's start off by a quick refresher of how this thing works and what HD video is, and is this thing even HD? And let's get into it. W-VHS records information onto 2 magnetic tracks, at least the video information. One of them represents PR and Luma, the other one represents PB and Luma. Then in the last video, I said that those get read off, they're RF encoded, they go through digital magic and component video comes out. It's the digital magic piece that I want to go into more detail today. And so what I did is I opened up the device and I found some nice tap points to tap both the RF signal coming out. Those are coming out of buffers and go out to my oscilloscope. Then these 2 large chips here, they demodulate the video. And I've taken the output of the demodulated signal just before it goes into the analog to digital converter, and I've tapped those as well. Had to cut a little bit of a hole in the side of the shielding to get everything to fit out nicely. I'll put up on my GitHub more details about how to do this modification if you have one of these devices and you want to repeat it, but you can see here the exact specific tap points. I connected those up to my oscilloscope. I was able to capture all 4 channels, and here you see just a raw capture of those 4 channels. So in red here, you have the 2 RF channels, main and sub, and in blue, you've got the demodulated. This is the hardware demodulated. Later on, we'll be doing some software demodulation. So that's what I mean by hardware versus software demodulation. Some things to notice here is you can see that there are 2 different sets of heads inside the deck, and they have slightly different levels. They sort of have alternating between which head is reading the RF signal from main versus sub. And if we zoom in a little bit more, you can see some scan lines, and obviously the RF signal still just looks like a wavy around noise. But if we zoom in even further, you can see that it is a sine wave moving back and forth. If you've casually been looking at the video traces, they look like HD video signals. Maybe they've got a single level sync instead of a tri-level sync. But let's go into answering the question, is this really HD? And if so, how HD is it? And how do they get HD images onto analog tape? So this is something that is decidedly not HD. This is NTSC, frame of NTSC. It's 480 lines of interlaced video. Typically it's digitized to 720 pixels wide. You can see blanking periods around it. That's the stuff in gray. And so you get about 500,000 pixels, quote unquote, per frame. And a lot of the video space, 23% of it, is dedicated to blanking. If you look at the other end of the spectrum, something I'd decidedly consider HD, which is 1080i or 1080p, you've got a 1920 by 1080 video. You still have that blanking period there, but it's about 16%. The other thing to note compared to, say, NTSC is that in component video, you get 3 fields happening. If you're talking about component, you're getting a sort of a wide channel, PB and PR, or an RGB, depending on how you're sending your component video. W-VHS lives somewhere in the middle. It is an image that is split up into luma and chroma. There's 256 pixels per line dedicated to chroma and 768 pixels per line dedicated to luma. It's a little bit more complicated than that, but we'll get there. The thing I really wanted to sort of show in these sort of series of pictures is, one, that it's sort of an anamorphic squeezing. You do lose horizontal resolution, even though it's presented on the screen as a widescreen image. Just from looking at a luma pixels perspective, it is 768 by 1032. The other thing to point out is you've really squeezed the blanking. I won't go into the details of why blanking periods exist, but if you look back at an NTSC, it has to do with the vertical sync and the electron beam having to retrace and a whole bunch of things. But in a more modern system, you really don't need that much blanking, and so you do have things like reduced blanking interval formats, and this is very much a reduced blanking interval. You've got a little less than 8% of the entire field dedicated to blanking. But there's more details. Each field, because this is an interlaced format, within each field, the lines in luma come from main and sub. So one line is for main, the next line down comes from the subhead, then main, then sub, and then main, then sub. Chroma, we'll get to in a second as to what it does. So in addition to the interlacing that you have, where you have a frame broken up into 2 fields, you get that further subdivided where the 2 stripes on the tape encode the odd and even lines per field, not per frame. So if we go back to our wires and plug them directly into our oscilloscope, and then we can use SCPI over Ethernet to capture and download the data, this is what the raw main and sub demodulated images look like. You can see that there are clearly distinctly 2 parts of the image. This is a test pattern. You've got the luma part occupying most of the space and then chroma off to the side. You can see in this picture that the vertical alignment isn't the same between the 2 fields, sorry, the 2 tracks, main and sub, but we're starting to see some video. Yes, there's some schmutz, I think that's the technical term, on the sub image. I think my heads need to be cleaned or something, but I'll do that before I take some high quality recordings. It's cool that we're just tapping 2 wires onto the board. Now, yes, it is the demodulated output, but here we can see some video image before any sort of digital magic happens. And the first thing we need to fix about this video, apart from cleaning my tape heads, is fixing the color. Typically, when you're recording raw images, you'll get a 444 chroma subsampling or no subsampling. This 444, 420 nomenclature can be a little bit confusing, but think about 4 pixels across, then how many of those pixels have color in the first row and how many of the pixels have color in the second row. In 444, in the first row, every pixel has color, and in the second row, every pixel has color. So there's a 1-to-1 mapping between the number of brightness pixels and the number of color pixels. Now, in a broadcast environment, they'll typically be sending their video around at 422. 422 is completely adequate for the end of the line of a broadcast recording, and so you'll have 8 pixels in 2 rows. In the top row, 2 of those pixels, 2 groups of those pixels will have color. In the bottom row, 2 groups of pixels will also have color. Now on YouTube and places like that, in highly compressed video, you're talking about 420. Now in W-VHS, they're squeezing some more blood from the stone, and they've gone to 620. So you have the alternating lines of luma encoded on the main and the sub head, and then each alternating line of chroma either encodes PB and PR. So they have to be combined together, so that in 2 lines, you only get 1 piece of information as to the color, and it's recorded at 1/3 the pixel clock rate of the luma information. So for every 3 horizontal pixels, 3x2 grid of horizontal pixels, you get 1 color, but you get the 6 levels of brightness. So I'm calling that 620. Another way of looking at this is sort of the chroma resolution relative to luma. As I said, 420 is what you might see on YouTube. NTSC has a completely different analog QAM encoding, and W-VHS is a little bit worse than that. VHS is worse again. And people talk about how great SVHS is from a color perspective, and it is because of the separation between the frequency in which the luma is encoded versus the color. You get less bleed, but because you have more resolution in SVHS, but you haven't changed the number of chroma samples, SVHS, on this metric at least, in resolution of chroma relative to luma, underperforms VHS. So all of these things seem pretty dramatic. You're losing a lot of color information, but it's important to remember how the eye works. Yes, having a lot of color is great if you're doing post-production and you're early in the pipeline, but as a final delivery format, you're going to someone's eye. You're going from screen to eye. And here we have a map of the rods and cones in the retina. Cones are responsible for color information. Rods roughly are responsible for black and white. There's differences in motion perception and other things. But as you can see here, most of your visual field is dedicated to brightness rather than color. But let's keep on moving on. So we saw what a raw frame looks like when it's decoded. Let's have a look at sort of the anatomy of a W-VHS scan line. If you've looked at analog video scan lines before, it'll look kind of similar. You've got a sync pulse sort of at the start of this image and then at the beginning of a new horizontal sync pulse at the end. The red period here represents the chroma and the blue represents the luma. And the raw pictures, despite being black and white and looking weird encoded, they looked okay. When you look at the raw demodulated images straight off my oscilloscope onto a computer program that just plotted them on a grid. But when you zoom in, you start to see some problems. You see some wibbly wobblies. These vertical lines should be straight. There's actually a fair amount of jitter, and you can see that jitter on a histogram here. And so I needed in my software to try and build sort of a PLL type thing that accommodated for the jitter and lined up all the frames, all the rows, so that you could get rid of the jitter, and I was able to do that. The other thing I noticed is that there's some offset between the V-sync between the frames, and you can then compensate that in code. You can see there's some digital data encoded in here. And then if you look in the red trace, and you can also see it in the blue trace as well, but it's more clear in the red trace, you get this interesting calibration pulse, which I haven't seen elsewhere in other standards, which looks like this. And this allows the device to take a reference of what black should be, what the mid brightness should be, and what white should be. The other thing that's going on is this time compression thing. I'm not going to spend a ton of time talking about that. They fit an entire one of those scan lines inside the same period, 63.5 microseconds, as an NTSC scan line to fit on the tape with the same tape head speed without having to have variable tape head speeds depending on what content you're playing back. And so the drum and the tape is operating at a pixel clock of around 17.2 megahertz. That's across main and sub, but then it gets decompressed by a factor of 1.2 to the 14.3 megahertz, which is written to and from the memory, the RAM in the device that then gets converted back to analog on the output. So if we step back for a bit, a W-VHS frame, so not a field, a frame of two fields contains 1092 by 1050 pixels of information. The fields come at 59.94 hertz, so roughly 60 fields per second or 30 frames per second. If you take 1092 times 1050 times 30, you get a pixel clock rate of 34.4 megahertz. That's the speed at which pixels arrive. Now, those pixels get divided onto two tracks on the tape. So each of those tracks needs to record a pixel clock of 17.2 megahertz. Now, the highest contrast image you can have in any particular scan line is an alternating set of black and white pixels. Black, white, black, white, black, white, 1 pixel each. That looks like a square wave if you're capturing that at sort of infinite bandwidth. But if you're capturing it at sort of Nyquist, so 2x, the largest frequency you can get is the fundamental frequency. And depending on your integration period, the analog filtering, your sample on hold and all that sort of stuff, but assuming best case for all of that, you get 2 divided by pi as the contrast ratio. That's the ratio between the area under a sine wave versus the area under a square wave. That gets you your 64% contrast. That's not the end of the story though. W-VHS is limited to a bandwidth of 6.6 megahertz. That sort of comes out of the way the tape heads work, the RF encoding and stuff that we'll get into in the second part of this video. So you're not able to capture the full 8.6 megahertz per track of analog bandwidth. We're not talking about pixel clock here, we're talking about analog bandwidth. So you're going to get at that 8.6 megahertz a combination of filtering from the low pass filter at 6.6 megahertz, plus filtering happening from losing the higher harmonics that are required to turn a sine wave into a square wave. So even though the image says it's 768 pixels wide from an active pixel perspective, it's really only roughly like 590-ish pixels because of the ratio of 6.6 to 8.6. That was a lot of numbers. Let's summarize everything that we've talked about so far in the HDness of W-VHS in sort of this one slide here comparing 3 different formats. For the column on the left, I've chosen 1080i 5994 at 422, perfectly adequate for final delivery. In that case, you've got 2 million pixels in an image versus the 792,000 in W-VHS and half of that roughly in DVD. But the effective dimensions, as we just discussed, are a little bit smaller because of the analog bandwidth constraints. And so I've picked the 589 number as being the effective number of pixels in a scan line for W-VHS. But you do also get some roll-off at the higher end of that as you approach sort of Nyquist. I'm calling the broadcast standard just reference in terms of signal quality. DVD, again, it's hard to make an apples to oranges comparison, but the raw bit rate, I believe, on a DVD is about 10 megabits per second. And so you need sort of roughly 12 to 1 lossy compression to encode your video. It's not as clean as a bandwidth roll-off and describing it that way, but you get to be smarter about what pixels you choose to throw out in the case of DVD, but there's still definitely compression going on. Then on color v Luma, with 422, you've got 50%. DVD is typically 420, so 25%. And W-VHS, again, is a little bit worse there at 16.7, 17% in terms of that. They say a picture's worth 1,000 words, so let's actually have a look. If you apply all the things that I've been talking about, so the jitter correction, stretching things out, a bunch of other little things, again, you can go look on my GitHub for the source code for this. This is what an image looks like once it has been taken from the demodulated path and corrected and all reassembled and put back together on the screen. Is it HD? No. Is it NTSC or PAL? Definitely not. Is it perfect? No. We've done a bunch of stuff to go from the black and white images you saw of the main, the recordings from main and sub. You can still see some of the noise and the dirt off the heads. You can see some speckling, but there's more that the system itself can do that I've decided not to implement. We haven't talked about it in this section of the video. We'll talk about it a little bit more in the RF section, but the W-VHS decks also do what's called vertical emphasis. That's a way of another way of doing noise reduction. Then there's temporal emphasis, which is looking from frame to frame. And then there's this Hadamard noise reduction, which is breaking the signal up into different bands and applying different noise reduction parameters to that. There are really 2 reasons why I haven't implemented all this. The first is that when I was implementing the horizontal emphasis, I had to do a lot of guessing to try and get the right parameters, and it was hard to tell whether I was making the image better or not. This stuff isn't documented to the level of detail whereby you can just copy and paste the parameters in and know you're doing the right thing. And I figured that would be the case with these other things as well. There's a lot of parameters I'd have to guess, and it would be a lot of work. And that's really the second reason is I didn't really want to spend months optimizing this. I wanted to use this video and the digging around that I've been doing to put together this material to give you more insight into the digital magic that I briefly mentioned into the last video. If you look at the GitHub, you can see the software, and it's all relatively straightforward to do with modern computers. You just take the alternating lines from main and sub, and you piece them all together, and you work out what the chroma should be from the main and sub channels of PB and PR, and you stretch it all out, and you make an image. And yeah, you've got to do some corrections and some noise reduction with de-emphasis, but it's relatively straightforward. That's all sort of ignoring the fact that we've missed the first half of the signal chain. All the video that we've been looking at so far and the signals we've been looking at have been coming from the demodulated output from the hardware demodulator on the W-VHS deck, but it needs to be demodulated. As you recall from the first video, it's frequency modulated signals that are being recorded on the tape. And so let's sort of recap what frequency modulation is and the three important numbers that sort of define how the frequency modulation works in the case of W-VHS. So frequency modulation, sort of like the name suggests, is you have a carrier frequency, that's a single sort of tone sine wave, and you shift that frequency up and down according to the baseband signal. And so there are three frequencies that are relevant here. There's the frequency, the largest frequency you want to represent in the baseband. In the case of W-VHS, that's 6.6 megahertz. Why it's 6.6, we'll get into a second. The second frequency that you want to talk about is the carrier frequency. What is, the neutral oscillating frequency of the RF signal? In the case of W-VHS, it's 9.25 megahertz. Then there's the deviation. How much do you change that carrier frequency in response to a change in baseband? And here we have a plus or minus 1.25 megahertz change corresponding to changes in baseband. So the sync tip is recorded at 8 megahertz as the RF signal, and the brightest white is 10.5 megahertz. And if you look sort of here in the time domain, you can maybe see the periods or the wavelength of the RF signal stretching and shrinking, but it's pretty hard to see in the time domain. But it's even harder to see in this example here, which is a 1 pixel wide white pixel in a field of black. I'm pretty hard pressed to see in the signal a move from 8 megahertz to 10.5 megahertz. But clearly video can do that. You can have a vertical white line on a screen and it'll appear. I'm including this example here as an illustration of the no free lunch that you get with FM encoding. We're trying to encode at least a 6.6 megahertz of analog bandwidth into a carrier whose frequency is changing only plus or minus 1.25 megahertz. Just stop and think for a second how you'd write an algorithm that would detect instantaneously a frequency change in a carrier, and then how you'd make it susceptible or immune to noise or just quantization error. In the video deck that I have here, we have 8-bit ADCs, there's noise from a variety of sources. It does an amazingly good job of doing a very tricky problem. And that's basically the story of this deck. They're really pushing all of the engineering choices to the max to get as much possible bandwidth out of this system. Anyway, looking at these charts in the time domain is not super helpful when it comes to FM, so let's look in the frequency domain. This is what the frequency spectrum looks like of the test pattern video that we've been looking at so far. This is looking between 6 and 12 megahertz on the x-axis, and the y-axis is power or magnitude in decibels. We can overlay on top of this what we talked about in this slide here of the three different frequencies. And in this overlay here, again, you can see the carrier frequency, you can see the sync tip down at 8 megahertz and the white peak at 10.5. And if you squint your eyes and you think about the test pattern image, it's mainly a field of 50% gray, so that's actually the peak, but you also see the sync tips and other things going on here. But obviously there's a lot more happening outside of this plus or minus 1.25 megahertz. And this starts to answer the question of why we're limited to a baseband frequency of 6.6 megahertz. If we look at this slide here, why only 6.6 megahertz? Here is a simulation using Bessel functions and things like that of a frequency sweep from 0 to 6.6 megahertz in the baseband, again encoded as a W-VHS FM signal, so a 9.25 megahertz carrier with the same deviation. And this blue big line here, this big area you see, shows large side lobes well outside of the 8 to 10.5 megahertz range. all of the information that you need to demodulate this signal is contained within the side lobes. And using what's called Carson's rule, which is sort of this rule of thumb for working out the side lobe width of an FM signal, you get sort of the majority of the side lobes being between 1.4 and 17.1 megahertz. So the reason why you end up with only 6.6 megahertz of bandwidth, analog bandwidth, when you'd like to have 8.6 to capture the full pixel clock, is basically the tape head gap, and the tape itself really can't record frequencies very well above 16 megahertz. And we're already above that with the 6.6 megahertz baseband frequency and the 1.25 megahertz FM deviation. You've got this trade-off. You could have a larger deviation, but then you'd still run into the same sort of 16 megahertz cap, and you'd give up the baseband frequency. So there's a lot of trade-offs that are happening. Another trade-off that's happening, it comes when you look at beta, which is, the modulation index. What is the change in carrier frequency compared to the baseband bandwidth? One of the reasons why you'd use FM, say for radio broadcasts, is noise immunity. That was the big motivation to move from AM radio to FM radio, is that when you're amplitude modulating signals, noise just is undifferentiable from signal. It's just a change in amplitude, and your signal is represented by a change in amplitude. So you have no noise immunity. When you do FM encoding, you get noise immunity, assuming you have a high modulation index. I think FM radio has a modulation index around 5. I probably should have looked this up. But you have high modulation indexes. In the case of W-VHS, they're really cramming that modulation index all the way down. It's like 0.2. So what's that, a 25 times lower modulation index than FM radio? That's because, again, you want to capture more analog bandwidth, and the environment going from tape head to tape head through the analog circuitry is a much lower noise environment than picking up a radio signal that's being transmitted from kilometers away. So you need to be able to recover from some of that noise, and that gets us onto the topic of preemphasis and de-emphasis. When you have a flat frequency spectrum of noise, just uniform white noise, and then you FM encode that, you end up biasing that noise towards higher frequencies. So what engineers worked out a long time ago is you boost in the baseband your higher frequencies, and so they'll be higher, hopefully, than the noise level. Then you deboost or de-emphasize the signal once it's come back from the tape deck, and therefore you're reducing the higher frequency noise, and you end up with a flat signal spectrum, but your signal to noise ratio is improved. Using sort of the numbers that I sort of back guessed here for a W-VHS of a tau of 150 nanoseconds, we go from a 9 decibel signal to noise ratio to 25 decibels, which is definitely an improvement. That then gets to the next question of, hey, if emphasis is such a good thing, why don't we do more of it? You run into the same problem again, which is you are increasing the frequencies in the baseband signal, and you run into the sort of tape limit around 16 megahertz. But this is a good sort of visualization of what emphasis is. Here in yellow, we have just a step edge in the time domain. In blue, we have what I think W-VHS does, which is about 16 decibels of preemphasis. And if you want to boost that up, double it again to 22 decibels, you run into the tape limit. So there's only so much you can do with preemphasis. So what else have I talking about here? I've got this slide here on frequency range versus head output. As a reminder, in the last video, I said, the reason why they're using FM is because of Faraday's law. You can't just directly encode your baseband on the tape because there's a lot of DC signals, and a DC signal does not result in a changing magnetic field. And, you physically, you attenuate all of that. And you can see that here at much lower frequencies. You get much lower voltage of head output here measured in decibels. And so you've chosen, or the designers here have chosen, a range that leads to about a 2.4 decibel variation in head output. And that's useful because one of the steps in demodulating an FM signal is a sort of a limiter stage. And if you have a very broad sort of envelope coming from the Faraday's law sort of transfer function, that limiter is much harder to design, but that's really getting into the weeds. I'm not actually going to show you my attempts of going from RF signal to a video frame, because they looked kind of crappy. And I'm going to hand this over to the much more knowledgeable folks over at the the VHS Decode project who can do this. But here I'll show you in the time domain. The blue channel, what you're seeing here, is what I recorded directly from the hardware demodulator on the tape deck. And the red is what I was able to do in software. And you can see I've got ringing, I've got overshoot, I've got undershoot. There was sort of this constant trade-off between pre-emphasis, de-emphasis, noise reduction, and filtering, and I couldn't quite get it right. And I'm happy to hand this project off to people who know what they're doing. All right, this has gone long enough. Thank you all for sticking around. I really do look forward to the comments that you might share with me. I've tried to compress all the information I've learned along the past week into this video, and just statistically, I've definitely made mistakes here. I'm looking forward to being corrected and learning more. I really enjoy people who comment on the videos, so please do that. If you've got more knowledge that you'd like to share, it'll benefit not only me, but the other people who read the comments. So please do participate. This has been a lot of fun. My hand seems to be doing much better. I don't think the blood has stained the tape deck too much. But yeah, I'll see you all in the next one. Bye.